Okay, so before this, you learned about substitution. And now I'd like to talk about how do we apply the substitution method if you have a definite integral, with bounds on the lower and the upper limits. So let's look at this specific example first. Evaluate the integral from 1 to 2 of x squared times the square root of x cubed plus 1 dx. So usually if you were just to do, your regular substitution without looking at the bounds, you would recognize that inside the square root you have this x cubed plus 1 function, and outside you have x squared, which coincidentally matches with the derivative of x cubed plus 1, which is 3x squared, right? Just differing by a constant. And so what we're going to do is we're going to use the substitution rule u equals x cubed plus 1. And this gives us du equals 3x squared dx. Right? And so remember what we have to do here. We have to rewrite the integral with your du, which is 3x squared, together with the dx, just so it's clear that that whole thing becomes your du. And then, well, we had to multiply by 3 to get to the correct term here. So we have to divide everything by 3 as well, so we don't change the function inside. And, well, the next step, now that you've written your integral in the form of, remember it was f of g of x times g prime of x dx, right? So this g of x is our u. Now we can proceed with the substitution. This becomes 1/3 square root of u times du, right? So that whole thing becomes du. Right, and so now the question is, what do we do with the bounds? Right? Do we keep them at 1 and 2, or do we change it to something else? And if you think about it, we're changing the variables here, right? We're not integrating with respect to x anymore, but with respect to u, which is a function of x. It's x cubed plus 1. So remember, this 1 and 2 here corresponds to x equals 1 and x equals 2. So it stands to reason that we wouldn't use 1 and 2 anymore, right, in this new integral that we have. And in fact, if you look at the graphs of these functions, this green graph right here is the graph of x squared times x cubed plus 1. All right, so that function. And the integral from 1 to 2 is this area here under the green curve in between 1 and 2. Now, if you look at the function we got when we did the substitution, which is this 1/3 times square root of u, I show that graph here. Well, look at the area under that curve from 1 to 2. Right? It's very, very small. Right? It's so much smaller than the actual value of the integral that we're computing. So what this is telling me is that keeping the bounds at 1 and 2 can't be right here. Right? Because I'm going to get a different value when I integrate that. And so what I need to do is to ask the question, when x equals 1 and x equals 2, what is u equal to? And, well, you have your substitution rule, right? It's x cubed plus 1. So we just take 1 cubed plus 1, that's 2. 2 cubed plus 1, that's 9. And use this as our new bounds, right? So think of this as transforming your whole integral from x to u, right? Including the bounds that you have. And now if you look at the graph here, what this tells me is that the area under the red curve from 2 to 9 is actually exactly the same as the area under the green curve from 1 to 2. Right? So this region has area equal to this region. And so now I can go ahead and integrate. This is therefore equal to, so that's 1/3 This u to the 1/2, so that becomes u to the 3/2. You divide by 3/2 as well. We don't need to say plus c, right? Because we're evaluating it at u equals 2 and u equals 9 and subtracting. And this gives me, what is that? 27. So, okay, I'm not going to compute that. You guys compute that. But yeah, so that's how you evaluate an integral with lower and upper limits using substitution. Right, so you get a number here. And the important thing to note here is that if you change the limits, right, when you do the substitution, you don't have to substitute x back into your integral. Right? Because you already have a definite integral with respect to u. And in fact, this is saying this integral is equal to this one, so you can just look at this one and evaluate that and be done with it. Now, I just want to talk about another way of approaching this problem, which is to look at the indefinite integral first, which is basically the same thing. Right, so it's x squared times square root of x cubed plus 1 dx. Without the bounds 1 and 2, well, you get the same integral after you make the same substitution, right? U equals x cubed plus 1, and du equals 3x squared dx. But now, if we ignore the bounds for now, when we integrate, so we get 1/3 u to the 3/2 divided by 3/2. So now we have that plus c over here, right? Because this is an indefinite integral. Well, now I can plug in my x function again, so x cubed plus 1 in place of u. And I get the general family of antiderivatives for my function. And, well, now I don't have to think about transforming the bounds anymore because I have the antiderivative. So now the integral from 1 to 2 of x squared square root of x cubed plus 1 dx is equal to, well, whatever this function is. Right, so x cubed plus 1 raised to 3/2 divided by 3/2. And you evaluate this now from 1 to 2. And now it should also be clear to you that whatever you get here, right, it's also going to be, right, a number, since it's a definite integral, and it's going to be the exact same thing that you would have gotten up here. Right, so in general, when you have to do a substitution where you have bounds on your integral, and you make the substitution u equals g of x, well, you take your a and you take your b, and you make the substitution as well apply to those numbers. You get g of a and g of b as your new bounds. And to end here, I do have another example, but I think I will let you guys figure this out yourselves. Right, so try this example and try both of the methods, right, that I talked about in the previous slide.